One. Okay, this is the first video in our trig review series. This is the first of 3. And what we're going to start with is the basics of trigonometry. Trigonometry is all about angles. So what's an angle? Let's take a look at this right here. Suppose I have a half line. So a half line is basically like that. I'm going to take another half line and I'm going to start it right at that vertex point there. And I'm going to make another half line so that they're attached at this point right down here. The measure this way between those two lines is an angle. We call that angle theta. All right, now, angles can be positioned anywhere, but what we're interested in is what's called an angle in standard position. And when we talk about an angle in standard position, we're talking about an angle that is positioned on the xy axis. So I'm going to try and draw an xy axis here. Now, when you measure an angle, you measure it from one of these half lines to the other. The beginning place where you start is called the initial side. The line where you end is called the terminal side. So an angle in standard position has its initial side on the x-axis. The terminal side is going to reside somewhere in the 4 quadrants. So if I put my terminal side here, like this, and we measure the angle from the initial side to the terminal side, I have what's called a first quadrant angle. Angles are measured counterclockwise in this setup. All right, so an angle measured in this direction is considered a positive angle. If I were to go backwards and measure it in that direction, I would have a negative angle. All right, an angle can be defined by the quadrant that its terminal side sits in. So this is a first quadrant angle. If I were to draw an angle over to here, right, and go from here all the way around, I would have a second quadrant angle, and so on, all the way around. All right, so that is how we're going to measure angles. Now, normally you think of angles, you think of degrees, right? So I have an angle that's maybe 30 degrees or 40 degrees or 120 degrees or something like that. And that's fine if what you're actually looking at is an angle. The thing is, trig functions are used to model real-world events. Anything that is cyclical, I gotta turn my phone down here. Anything that is cyclical can be modeled using a trig function. And the problem is, we need real numbers. Degrees are not real numbers. Degrees are artificial. All right, it's just a way of breaking a circle up into 360 pieces. If we're going to use trig functions to model real-world events, we need real numbers. All right, and real numbers are radians. Radians is what we'll be using for the remainder of this class, and radians are what you're going to be using in calculus. All right, so we need to look at what is a radian. Now, I'm going to start with actually a diagram from the book. This is on page 366 in your book, just because the book can draw circles better than I can. So we have a circle, right? Any circle. And I draw what's called a central angle. So we have the center at the center of the circle, and we have the two half lines intersecting the sides of the circle. Now, if the radius of the circle, here it's r, is the same as the length of the arc that is subtended by the two angles, by the two lines, then the angle between them is considered to be 1 radian. Now notice, this is not dependent on the size of the circle, as long as the ratios are the same. I can take a larger circle, right? Here's my smaller circle over here, right? I can take a larger circle, and notice it doesn't change, the angle doesn't change. the length of the arc changes, which means the radius changes, but as long as the radius and the length of the arc are the same, the arc sweeps out 1 radian. Now, we can use this here to define a circle. Now, when we're looking at arc length is exactly the radius of the circle times the angle in radians. So when I have 1 radian, right, I have a radius of r and I have an arc length of r. All right, arc length is usually defined by the letter s. All right, so if I come over here, arc length s is r times the angle theta, where theta is in radians. Now, I need a way to relate degrees to radians, because degrees are familiar, radians are not. So in the beginning, you're going to need to be going back and forth. So what else do we know about a circle? Well, I know the circumference of a circle, right? The circumference of a circle is pi times the diameter. The diameter is twice the radius. So that is 2 pi r for the circumference of a circle. Now, if I look at my arc length, right? If I look at my arc length as being the entire circle, let me see if I can draw a circle here. I guess I can sort of draw a circle there. Okay. All right, so I look at my arc length as being the entire circumference of the circle there. All right, that means S is 2 pi r. 2 pi r. All right, that is equal to r theta. All right, so 2 pi is the angle involved in an entire circle. So once around the circle is 2 pi. But I also know that once around the circle is 360 degrees. So that gives me a conversion ratio. 2 pi is 360 degrees. Now, if I divide both sides of this by 2, I can simplify this ratio a little bit. Pi is 180 degrees. And this is our conversion factor. All right, this is what we're going to be using to convert between degrees and radians. Let me get a clean page going here. Hang on a second. All right, so if we start with our conversion factor, 2 pi equals 360, and then pi equals 180, all right, then what I can say is this. This side is radians, right? This side is radians, this side is degrees. So pi radians equals 180 degrees. If I divide both sides of this by pi, then 1 radian is 180 over pi degrees. And if I come back over here, and divide both sides by 180, then I get pi over 180 radians is 1 degree. And this is how we convert back and forth. To convert from degrees to radians, I'm going to multiply by pi over 180. To convert from radians to degrees, I'm going to multiply by 180 over pi. All right, so our conversions are this: degrees to radians, we multiply by pi over 180. Radians to degrees, we multiply by 180 over pi. All right, so if I have an angle that is 30 degrees, and I want to convert that angle to radians, I am going to take 30 degrees, multiply by pi over 180, and then reduce my fraction. All right, so that is going to be pi over 6. All right, radian measure is written either as a decimal or as a fraction multiple of pi. Exact values are written as fraction multiples of pi. Now, there are a few of these that you're going to need to have memorized, that you're going to need to know. All right, and we're going to build up that, that library here in just a minute. Let me, give me 1 second here. All right, so I'm just going to go through the book here real quick. Here's the conversion factor on page 368. All right, so you can take a look at that. Now, if I want to do some conversions, all right, take a look. They've got some angles there. 150 degrees, right? 150 degrees in radians is going to be 150 times pi over 180. And again, reduce the fraction. You don't want to turn this to a decimal. You want to reduce the fraction. All right, so that's going to be 5 pi over 6. If I want to go the other way, suppose I have, let's say, pi over 4 radians, and I want to change that to degrees. All right, I'm going to take my pi over 4, and I'm going to multiply by 180 over pi. All right, which is going to give me 4 into 180 is 45. 45 degrees. All right, there are some conversion problems in this section that I'm going to want you to take a look at. Now, there's a little chart here. You should know this chart. All right, we're going to, in a couple of minutes, I'm going to go through the unit circle model, and you'll see where all this is coming from. But the table 1 on page 369, these are the radian measures that you should be able to just pick out. All right, these are the angles that are going to be important to us across the top here in degrees, and their radian equivalents. All right, so from this section, I'm going to pass by this stuff right now. All right, so from this section, what I'm considering to be important are problems 11 through 58, it looks like, there. All right, so this is the point at which you might want to pause the video and work on some of these conversions, just converting back and forth from degrees to radians. Okay, assuming you're back after pausing and trying some of those problems, I'm going to move into the next section, which are the trig functions. All right, now here's where this is going to get a little tricky for me because I have to draw this all. All right, again, I'm going to start with a diagram from the book, which is down at the bottom of page 377 here. All right, let me get a clean page here going to. Okay. All right, so we need to define the 6 trig functions, that is sine, cosine, tangent, secant, cosecant, and cotangent. Now, there is an actual arithmetic way to define them that you may or may not have seen before. All right, and this involves a circle of radius 1. So if we look over here, if I can get there it is. All right, if we look over here, all right, we've got a circle of radius 1. We're going to take a line that is tangent to that circle. That means it touches it in one place, and that one place is at the point 1, 0. All right, so we do that, and then we have this line that represents a line of real numbers. All right, and we take a point on that line. They're labeling that point right there, T, right? And we wrap it onto the circle so that it falls onto somewhere on the circle, anywhere on that circle it could fall, all right? And we label that point XY, all right? Now, X is going to be the cosine of T, and Y is going to be the sine of T. And that is how we're going to define our 2 main trig functions. All right, so sine of t and cosine of t lie on this unit circle here, this circle of radius 1. Now, if I move over a page, All right, we have all the definitions. Rather than me rewriting them, I'm just going to leave them sit here while I talk. All right, so you have t as a real number that sits on that line that is tangent to the circle. We define each of these functions. Now remember, this is a definition. It's not something we're deriving. All right, we define the sine of t to be the y-coordinate. We define the cosine of t to be the x-coordinate. All of the other trig functions are defined based on the relationship to x and y, sine and cosine. All right, so tangent is y over x, cotangent is x over y, cosecant is 1 over y, secant is 1 over x. All right, we can define all 6 trig functions in this manner. All right, now, when we move on to the unit circle, at this point, I think I can make a useful diagram here. When we move on to the unit circle, all right, so remember, this is a circle of radius 1. All right, and I have my point here, which is coming from that, right, that line that gets wrapped around onto the circle, right? This value t ends up being the length of the arc here. All right, since the radius is 1, the length of the arc is the same as the angle, theta. So that means I can make a change of notation. All right, t, right, this is the value up here, t is simply theta in radians. All right, so when I say sine of t, when I'm looking at t as being up here, once I slap that down onto the circle there, we're looking at theta, so sine of theta. All right, so on the unit circle, you would say sine of theta is y, cosine of theta is x, like that. Okay, now we're going to use this unit circle to define some values for sine and cosine. Now again, you've probably seen this before, maybe not in exactly this way, all right, where you need to know things like the 30, 60, 90 right triangle, the 45, 45, 90 right triangle. All right, this is another way of looking at that. It also expands it so that you're not just looking at a single triangle, but you're looking at all 4 quadrants. So, the basic idea here, once we've made the conversion over to radians, all right, right here, right? Once we've made that conversion into real numbers, radians, what we need to do next is to build up our library of triangles. All right, so I'm going to start with the 2 basic ones. I'm going to start with the 45, 45, 90. All right. Now again, none of this should be new information. I'm hoping I'm just presenting it in a way that you might have seen it before. Okay, so there's the 45, 45, 90 triangle. Now remember, the ratio here is 1, 1, square root of 2. All right, since we're dealing with a unit circle. All right, so let's see. Does anybody actually remember the rules for sine, cosine, and opposite sides and adjacent sides? And I'm waiting to hear half the class yell. SOHCAHTOA, right? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. All right, so dig that out of your high school vocabulary there. All right, so when I look at a 45-degree angle, let's say, I look at the sine of 45 degrees. All right, let's take this as the 45-degree angle. right? I'm looking at the opposite side, right? The side opposite over the hypotenuse. All right, so that is 1 over the square root of 2. Or rationalize square root of 2 over 2. All right, how about the cosine of 45 degrees? Well, that would be adjacent over hypotenuse. So adjacent would be adjacent over hypotenuse, which is again 1 over the square root of 2, or rad 2 over 2. All right, so when I'm looking at sine and cosine as the x, y coordinate on a unit circle, right, that coordinate on the unit circle would be square root of 2 over 2, comma, square root of 2 over 2. Now I'm going to put that on the circle in a minute. I don't have enough room to do it all right here. All right, what about the other standard triangle that we have, which is the 30, 60, 90 triangle? All right, so the 30, 60, 90 triangle looks like more or less like the, okay, well, pretend that's triangular. There's my right angle. All right, so we'll put 30 degrees up here just because that one looks smaller, and 60 down here. And remember, the ratio for this one is 1 to square root of 3. All right, so the hypotenuse is 2, and then smaller side is opposite smaller angle. All right, so it looks like that. All right, so let's start with sine of 30 degrees. Again, 30 degrees. Sine is opposite over hypotenuse, so that's 1/2. Cosine of 30 degrees. Again, 30 degrees. The cosine is adjacent over hypotenuse, so that is rad 3 over 2. So as a point on the unit circle, that would be square root of 3 over 2, comma, 1/2. Again, cosine, comma, sine. How about 60 degrees? Sine of 60 degrees. All right, here's 60, so sine is opposite over hypotenuse. So that would be rad 3 over 2. And cosine of 60 degrees. 60 degrees, that would be adjacent over hypotenuse, would be 1/2. So as a point on the unit circle, this would be 1/2, comma, rad 3 over 2. All right, so notice there is definitely a relationship between these two because they both come off the same triangle. Now, to set up a unit circle, we have to take the circle, break it into quadrants, so that's 4 parts, between 0 and 2 pi. All right, so a lot of people have trouble counting out the angles in radians. So I'm going to show you a little trick before I move on to a blank page and do this. Let's look at a number line. All right, and let's say my number line starts here at 0 and ends over here at 2. If I split this number line in half, it's at 1. If I split it in half again, that's 1/2. And this is 1.5, or 3/2. All right. Now, let's stick in this first. Now, notice I have quadrants here. Okay. If we stick in this first quadrant and I break this in half, I am at 1/4. All right, so this is 0, 1/4. 2/4 would be 1/2, so this is going to be 3/4. 4/4 would be 1, so this is going to be 5/4. 6/4 would be 3/2, and so this is going to be 7/4. And then 8/4 would be 2, so I get nice even markings in there. Now, I'm going to come back to this. I want to go to a blank page. Hopefully I got enough blank pages here. Turn that one off, turn that one on. All right, now we're going to draw a big circle here. Hopefully with enough room to actually fit everything in that I want. Okay. Yeah, I don't have my tools to erase that. That's okay. We'll deal with it. All right, and I'm going to put an XY axis right through here. And we're going to call this 0. All right, so think about the number line that we just did. We started at 0, and then it went all the way around to 2. So think about multiplying everything by pi now. So that would now be 2 pi. All right, so what was this? This was 1/2, so that's going to be pi over 2. This would be 1, so that's going to be pi. This was 3/2, so this is 3 pi over 2. And then we're back here at 2, or 2 pi. All right, so the first thing I did was to cut each of my quadrants in half. And we called that 1/4, so that is going to be pi over 4. This one was 3/4, so that's going to be 3 pi over 4. This one was 5/4, so 5 pi over 4. And this one was 7/4, so that is 7 pi over 4. Now we saw before, a few pages back, that pi over 4 is 45 degrees. All right, every single one of these angles with a denominator of 4 is a 45-degree angle. All right, if you have an angle in radians in lowest terms and the denominator is 4, you have a 45-degree angle. Okay, it's important that the fraction's in lowest terms. All right, but pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, 9 pi over 4, 27 pi over 4, 39 pi over 4, right? Anything like that that's in lowest terms with a denominator of 4 is going to be a 45-degree angle. All right, and we saw from the 45-degree angle that both the sine and the cosine were rad 2 over 2. Rad 2 over 2, rad 2 over 2. All right, now what is the difference between this 45-degree angle pi over 4 and this 45-degree angle 3 pi over 4? Well, it's the quadrant that it sits in. So in the first quadrant, both x and y are positive. So both x and y are positive here. In the second quadrant, x is negative, y is positive, but it's still a 45-degree angle, so the values are the same. All right, so this is going to be x is negative, y is positive. All right, down here, this is still a 45-degree angle. All right, the difference again is the signs. Down here, both the x and the y are negative. Over here, the x is positive and the y is negative, so that makes that rad 2 over 2, comma, negative rad 2 over 2. All right, so now what did I just do? Well, if I want to know what the sine of pi over 4 is, I can look over here and say, okay, sine is y, so the sine of pi over 4 is rad 2 over 2. If I want to know what the cosine of 5 pi over 4 is, well, cosine is x. All right, so that's right here, negative rad 2 over 2, and so on, all the way around. As long as I know which of these 4 angles I've got, I know which quadrant I'm in, and I know the sine pattern. So I know the value of sine or cosine for any of those angles. Okay. All right, now I can do the same thing with the, I can do the same thing with the 30 and 60 degree angles. All right, if I come back here to my number line. All right, 30 degrees, I'm sorry, 1/6, we figured this out before, right? 30 degrees is pi over 6, so 1/6 would be on this side. 2/6 or 1/3 would be on this side. All right, so if we use, because these both come off the same triangle, if I use 1/6 to count, 0/6, 1/6, 2/6, 3/6, 4/6, 5/6, 6/6, 7/6, 8/6, 9/6, 10/6, and 11/6, and then 12/6. All right, so I can fill those fractions in there. And then if I come back down here now and look at my unit circle, basically what I just filled in was my 30-degree angle, which is pi/3. I'm sorry, pi/6. And my 60-degree angle, which is pi/3. All right, now I can fill in all the other ones here again, just like I did on the number line, by counting. Actually, if I can draw the lines sort of straight, let me draw them in first. By counting by sixths. Right? And when I do that, I have all of those values filled in. All right, so 1/6, 2/6, 3/6, 4/6, that was 2/3. What did I just say? 4/6, 5/6, 6/6, 7/6, 8/6, that's 4/3, 9/6, 10/6, and 11/6. All right, so now I have all the 30 and 60-degree angles filled in. Now we figured out that the sine and cosine for a 30-degree angle, cosine is rad 3/2, and sine is 1/2. And up here, it was the other way around, right? Cosine was 1/2, sine was rad 3/2. All right, and then I can fill in all the rest of these using the same sign pattern just by looking at the denominators. So, just like with the 45-degree angles, if I have an angle in radians in lowest terms whose denominator is 6, I have a 30-degree angle. All right, so this is my first 30-degree angle. This is my second 30-degree angle. All right, but I'm in the second quadrant, so that means the x is negative. Oh, that's a 3. All right, over 6. So here's my next 30-degree angle. All right, but down here they're both negative. All right, over 6. So here's my other 30-degree angle. Here the x is positive, the y is negative. All right, and then if I have an angle in radians, again in lowest terms, whose denominator is 3, I have a 60-degree angle. All right, so 2 pi/3 is my 60-degree angle. All right, over here again, x is negative, y is positive. Where do I have another one? I got another one down here, right? 4 pi/3. Down here, they're both negative. And then I have one right here. All right, where x is, hang on a second. Where x is positive and y is negative. All right. All right, now the only thing I haven't filled in are the actual axis points, but remember, this is a circle of radius 1. All right, so the axis points are exactly what you would expect them to be if you're crossing an axis with a radius of 1. All right, so I'm gonna point you to a download for a better copy of this unit circle. Don't try and use this one; it's kind of messy. All right, but basically what we have is we have our coordinate points as cosine theta, comma sine theta. All right, so if I can find the sine and cosine of an angle, I can find every other trig function because there's a relationship between the trig functions, all right, because of the way they were defined. All right, so let's take a look at that relationship. Too far. Let's take a look at that relationship. And let me get up a blank page here. All right, so the relationship that we have is this. So we have sine theta, we have cosine theta. Tangent theta. We define tangent to be y over x. So that is y is sine theta divided by cosine theta. All right, cotangent theta we define to be x over y. So that is going to be cosine theta over sine theta. Right? Secant theta. We define secant theta to be 1 over x. So that is 1 over cosine theta. And cosecant theta we define to be 1 over y. So that is 1 over sine theta. All right, so if I want to find all 6 trig functions for, let's say, the 30-degree angle. Let's go for something simple. All right, so 30 degrees, or pi over 6. Right, what do we already know? We already know what the sine of pi over 6 is, right? The sine of pi over 6 is 1/2. The cosine of pi over 6 is square root of 3 over 2. So what if I want the tangent of pi over 6? Well, that is sine over cosine. So that is 1/2 over rad 3 over 2, which is going to reduce to 1 over rad 3. When you rationalize it, rad 3 over 3. Let's go for cosecant of pi over 6. Right? Cosecant of pi over 6 is 1 over sine. So 1 over 1/2, or 2. Secant pi over 6. All right, that is 1 over cosine. So that is 1 over the square root of 3 over 2. 2 over rad 3, or 2 rad 3 over 3. All right, how about cotangent pi over 6? Well, that is 1 over tangent, or cosine over sine, right? Because we have it written here, right? So it's a reciprocal of tangent. So I'm going to write it that way. All right, cosine over sine, which is going to reduce to rad 3. All right, so all I need is sine and cosine. If I have sine and cosine, I have everything. All right. Okay, what else can we get out of this section here? I think there's a couple of good tables here. All right, on page 381, you might want to take a look at table 2. It has some information that is helpful, and I think I'm moving into the next section at this point. Okay. All right, so let me pull out of this. And we're going to pass. Oh, you know what? I think I'm going to stop this video and put the rest of this on the next one. Give me just 1 second here. For this section, this is section 6.2. Take a look at the problems that are on page 389, numbers 13. I'm going to say 13 through 84. Now, I do need to point out one thing here. If you're working with unit circle values, you're fine. If you're not working with unit circle values, then we have to resort to the calculator and a decimal. All right. Any of the values that fall in the unit circle, denominator of 6, 3, or 4, all right, or whole values, are going to be done as exact values. But take a look here at 65 through 76 in particular. All right, you have odd angles, right? 14 degrees, 28 degrees, pi over 12, things like that. All right, those are not, you're not going to get exact values for. So in order to evaluate the trig functions for those, notice it says use your calculator and approximate to 2 decimal places. So if I pull out the calculator here, let me turn that on. All right, the mode that your calculator in is important here. Now, if you hit the mode key, right, the mode key right there, you'll see it's a little blurry, but right there it says radians or degrees. Right, you need to make sure you're in the right mode for the type of angle you're dealing with. If I'm dealing with an angle in radians mode, I need to be in radians mode. If I'm dealing with an angle in degrees, then I need to be in degrees mode. All right, so let me get up a clean page here. So let's say I've got 2 different problems here. All right, let's say I want to evaluate the sine of pi over 12. All right, and then maybe I want to do the cosine of 21 degrees. All right, for me to evaluate on the calculator the sine of pi over 12, I have to have my calculator in radians mode. Mine's already in radians mode. All right, so I'm going to exit out of this. All right, now notice here you've got sine, cosine, tangent. All right, those are the only ones you have on your calculator. You need to use the reciprocal functions, or those ones that I just went over, to evaluate any of the other trig functions. All right. Okay, so sine of pi over 12. So I'm going to hit the sine key. There's a pi key right above the little caret right up there. So I'm going to go second pi divided by 12, close the parentheses, that's optional, and hit enter. All right, so see what I get there. I get a decimal value, 0.25, let's say 0.2588. We'll stop there for that. That's just what that looks like. All right, there's no nicer way to write that. Now, if I now want to go on and evaluate cosine of 21 degrees, I have to change the mode on the calculator. So I go into mode, and I tab down so radian is blinking, move over to degrees, and hit enter. And then come out. And then I can do cosine of 21, just like that. Hit enter. All right, so what I get there is 0.9336 rounded off. Okay, you're going to be spending a lot of time moving back and forth between degrees and radians from now until the end of the semester. All right, so get used to that and make sure you can see up on top. Notice, depending on how old your calculator ROM is, you'll see up here which mode you're in. All right, if you've got anything close to a newer version of this, of an 83 or an 84, it'll tell you up here you're in degrees. Make sure the mode you're in matches the problems you're doing. All right, so you can take a look at the problems on page 390, that problem set that I just said, and we'll pick this up in the next video.